Good evening, 7:30. Let's get started. So let's see. We are on day 4. So we already started on the Boolean algebra, right? I hope you guys has reviewed that. Also, we didn't go through that previous one, lecture 3, digital synthesis and number system. Let's start with that one, digital system, number system, synthesis and number system. Any question on that part or any other question? No? Okay, then in that case, let us do this problem. Screen. Okay, so problem is like this. We have a number system called mu note that uses symbol do, re, mi, fa, sol, la, ti with that decimal weight equivalent to that 0, 1, 2, 3, 4, 5, 6 respectively. So do is 0, re is 1, mi 2, fa is 3, so is 4, la is 5, and t is 6. Now we are given a value written in the mu note system, mi, re, re, do. Now what is the decimal value for that one? And the other problem is that, let's say we have a decimal value like 1045673. What would be the mu note representation of this specific decimal value? So that's the problem we want to do. And let's do it in a group. So let me create a breakout rooms for maybe 20, 4 to 5 participants. Any question before we go to the breakout room? Oh,
Is
yeah.
is decimal weights equal to like the value of those symbols?
Yes, values of those symbols. Okay, so let's take 10 minutes to solve this problem and we'll be back with the solutions. Someone or some group need to present the solution. Okay. All right, I'm opening the room for you, 10 minutes. Okay, let's wait for others to join in from the breakout room to here. And let's cross check our results. Yeah, I think we have all of us back to here. So anyone wants to share the result for 1A, the first
740,
problem?
742.
742. Yeah, correct. So do you want to explain what did you do? Can you please explain to others? The answer is 742. That's correct. So this one. So what was the step? Anyone wants to explain that?
I can do it.
Okay, sure.
Oh. Okay, so I basically converted mi, re, do, and using the decimal weight for each one. So that means mi would be 2, and then re would be 1, re would be 1, and do would be 0. So and then that's all in base 7. So after that, I did
Why base 7, Akash?
it's because there's like 7 numbers basically, or 7. It's like decimal weight is 10 because there's 10 digits, and then there's
Right.
like hexadecimal is 16 because there would be 16, and then this one would be 7 because there's 7.
Right, because there are 7 symbols on the problem. Yes, please go ahead.
And then after that, I started from the least significant bit, and then I did 0, which is 0 in this case, and then it was 0 times 7 to the 0th power, and then I moved the other way, 1 times 7 to the 1 power, and then 1 times 7 to squared, and then 2 times 7 cubed. And then after that, I added all of them up, and then that was the answer.
Okay, so everybody followed up, Akash, on that part? So basically what he did, he basically look at the positional weight because we have the 7 symbols here. So it is of the base 7, and then we have these each symbol mi, re, do that has equivalent value of 0, 1, 2, 3, etc. Right? So we basically pick up those symbols value, place there like 2, 1, 1, 0, and then each of them is multiplied with the positional weight. So base 7 to the power 0, first position. Second position, 7 to the power 1. Third is 7 to the power 2, then 7 to the power 3. So it is basically, then we add them up, those multiplication values. So 7 cubed plus 1 multiplied by 7 squared plus 1 multiplied by 7 to the power 1 plus 0 multiplied by 7 to the power 0, which is comes down to 742. Question on this part from anyone? Okay, who wants to go for the next one? We have a decimal number. We want to convert it into the mu note notation.
Do you want the step-by-step or the answer?
Let's first go with the answer.
I got re, re, ti, re, fa, so. Sorry, was that too fast? Fa, so, re, ti.
Re, ti. Okay. So others, do you agree
Oh,
with this?
there's a re in between ti and fa. Sorry.
Oh, okay, okay. Re is right here. Okay. So re, re, ti.
Oh wait, no. I'm
Re.
sorry. I'm just gonna repeat it. I think I went too fast. Re, re, ti, re, fa, so, re, ti.
Oh, okay, okay. Re, re, then ti, re, fa, so, then re.
Yeah, and then ti.
Okay, okay. And can you explain how did you get that?
Since we already know the music notes, or what's it called? Mu note is 7, base 7. All we have to do is we start out with 1,045,673. We divide that by 7.
Okay.
And we keep the answer while we keep the remainder on the side.
Okay.
The remainder would be 6, and the quotient or whatever would be 149381.
Okay. Mm-hmm.
And then we would continue and take that 149381 and divide it by 7 once again, and keep the answer and the remainder.
Okay. I think.
And then we would repeat that.
Okay. So this is like maybe 21340, right?
Yeah. And the remainder would be 1.
Then 21340 division 7. That would be about 3048.
Yep.
Remainder
4.
4. And then we pick up 3048 divided by 7, which is 435. Remainder would be 3. Then 435 divided by 7, which would be 62. Remainder is 1. Then 62 division 7, which is about 8. And remainder 6. And from there, okay, sorry, I'm out of the space. From there, it's 8 by 7. Quotient is 1, remainder is 1. And then 1 by 7, quotient 0, remainder is 1. So basically, we stop the process till we reach the quotient value to 0. And then we mark down this remainder symbols, like 6 corresponds to T according to our step, right? And 1 corresponds to re, 4 correspond to so, 3 correspond to fa, 1 corresponds to re, 6 corresponds to T, 1 corresponds to re, and 1 corresponds to re. So now what we do, we write the number from end to beginning, like this direction. That's why we get re, re, ti, re, fa, so, re, ti. Okay, is that clear for everyone? Question? So now, if there is no other question, then let's do one more problem. It's like that. Okay. Who wants to answer this one? Represent a value 12 in decimal into a 4-bit 2's complement representation.
First, you have to find out the range of 4-bit 2's complement, and the range formula is 2 to the n negative 2 to the n minus 1 to 2 to the n minus 1, and then outside that exponent minus 1.
Okay.
And if the value 12 is inside that range, then you can continue with converting it to 4-bit 2's complement.
Okay, so what's your answer there?
My answer. So I think
So for this guy, what is the range? 4-bit.
For this one, the range is since it's like that. So n is equal to 4, so it will be 4 minus 1 equals 3, so it will be negative 8 to 7.
Right, exactly. That means the conclusion is that we cannot represent this value 12 with this format, 4-bit 2's complement value format, because this range is -8 to 7. We can represent values only between -8 and 7. Is that your answer?
Sorry, shouldn't that be +2 on the right?
+2? Oh, sorry. Yeah. Yeah,
okay,
yeah.
cool.
Thank you. Yeah. This one is 2 to the power 3. Yeah. Thank you.
Yeah.
And just in case anyone else is looking at it in the future, also on the one above it, right?
Come again? Sorry, I didn't get that.
Just in case somebody's looking at it and is confused, the one on top, right, as well? Or am I being stupid? No, okay, cool.
Yeah. So, okay. So for this type of problem, dealing with the 2's complement, this number of bit is really important. Like, let's say if someone asks that, hey, go and change, like represent 5, let's say 5 in 2's complement form, right? Represent 5, 2's complement. So one can come up with an answer like, okay, it is 101 base 2. But that's not true. Like, let's say we are talking about a 3's complement, 3-bit 2's complement. In that format, 3-bit 2's complement, this guy is a negative number. And in fact, this represent in that form, it represents 3 bits, right? So 4 minus 1 minus 3. It's not 5. So it is very important that in the problem, this number of bit is specified. If it is not specified, correct answer would be cannot be done. Cannot be done because there is insufficient information. Question on this part? Okay. So that was for the last day's topic of the these number systems and the digital synthesis, etc. And today's topic was we started with the review of the Boolean algebra, right? Boolean algebra 1. This is basically a review from your CS147 study. And this one, maybe let me just pull out my poll about your preparedness for this today. So I'm launching the poll, about 1 minute, just answer it. You can do it anonymously. if you want.
Does this include the lecture videos for the labs too?
What's that? Come again, sorry.
So the poll, does it refer to the lecture videos for the labs too? Like the
no, lab is kind of in your own pace. It's for your own purpose for the project. Otherwise, you'll have hard time to project if you don't follow the labs. But yeah, it's for mainly on the lectures.
Thank you.
I had a question about lecture notes versus videos. Do they both cover like the same content, like in notes as in videos, or are there differences between them?
The notes sometimes have an extra explanation. So it's basically, yeah, it will be good to actually do it in side by side, watch the video and go through the notes in the slides. Sometimes it has some extra informations.
Okay.
Okay, I have, yeah.
I had a question about Project 1. I think you posted an announcement today about Project 2, and you mentioned ungraded milestones for it.
Mm-hmm.
I was wondering, do we have any milestones for Project 1?
No.
Any guidelines?
One is very simple.
Okay.
Okay, so we have 81 out of 87. Maybe, okay, it's 2 minutes past. Okay, I'm closing the poll and sharing the result. So 57% watched the videos for today's topic. All of them, that's good. And let's actually make this percentage more and more for this class. Otherwise, you'll actually left behind. Reading notes is also good, 67%. Please keep it up. And for others, please make sure you review the topics before you join the class so that you would be on the same page with the others and you understand those discussions and everything. Question wise, you need to practice generating questions. You need to be curious, little more curious, okay, about things. So definitely these lectures and this course won't give you the entire story of the computer architecture. There are 247 and all other advanced courses. We're just scratching on the surface, basically on this specific subject. So I hope you will be a little more curious and you know, like generate more and more questions, okay? And which I hope to be beyond also this scope of this course as well. That's how we basically progress. Anyway, about today's review, right? The Boolean algebra 1. Any questions from that? No? Okay. So what shall we do? And where is my, oh, there is my Zoom session. Okay. Okay. Since we have some time and we don't have a theoretical things to do right now, let me introduce you some of the Verilog things like a get level modeling. I hope I have the license for the models. Just hold on. So what I'll do, I will basically show you that with the logics and truth table and everything, you can actually start modeling them inside the model sim. And this will be useful in your project 3 when we start implementing some get level like circuit design there. So let's see. Okay. So just bear with me a little bit. Okay, let's see if we can implement and see the function, Boolean function xyz equals x. Oh, am I sharing? No, I'm not sharing, right? Okay. Share my screen, screen one, share. Okay, so so let's have a Boolean function like x, y bar, or z. And we want to see if we can actually implement that in Verilog and model theme environment. So to test this function, we need to come up with a truth table, right? So x, y, z, let's write it down, and the f, and 0, 0, 0 is 0, 0, 0, 1 is 1 in this case, then 0, 1, 0 is 0, 0, 1, 1 is 1. Okay, and let's copy this. We 1, 1. Okay, and the function would be, this is 1, 1, 0, 1. Okay, so this is the truth table for this function, and we're trying to implement that in Verilog. So what we'll do, we will start with a project, maybe new project. Yes. Okay. So maybe CS147. Under that, make a new folder, name Verilog modeling. Okay, so let's check that. And project name, let's say get level modeling. Okay. Add to project, a new file. Let's say Verilog, and let's say name myfunc v. Okay. So I hope everybody can see my screen now.
Yeah, looks good.
Time scale 1 PS. Okay. Module. So this is the function. Okay, this is the function I want to implement. Let's have, it's called myfunc. X, Y, Z. and module. Whether it may have syntax error and everything. I don't code in Verilog every day, so we'll figure out. Input x, y, z. Let's make a function output f. Okay, function output f. Okay. So basically, in this function, from logic gate perspective, from this function logic gate perspective, what we want to do is this, right? So this function on a logic gate scale, it is becoming like a AND with X and an inverter with Y, and that is connected with Z, and this is my F. So this is the one I want to implement in a Verilog level. So what we need, X, we need something somewhere like this one, let's say W1, and let's say W. Oh, sorry. Yeah. So we want to implement this function, Boolean function. That means we are basically looking at an AND gate, an inverter, an OR, and let's say these, we need to have some intermediate words to carry on the intermediate logic values. Let's say this is W1 and W2. So that means we need to have some word here, W1, W2. Now here I can do something like not. This is a get type followed by maybe a name of the instance. We call it an instance name. So we are naming this instantiation of the not as inverter 1, which has a output W1, which has a output W1. Let me just. Output of W1, and input is Y. Then my AND, let's say the instance name is AND1. You can give any name there, and this, let's say this is OR1. Okay, so AND 1. So this is output to W2. This is output to your W2, AND's output. So that's what will become W2, and input is X and W1. And then we are looking for the OR. So let's say OR1. Its input is W2. Oh, sorry. Oh, yeah. Output is F. Input is W2 and Z. So that's the Verilog description of this Boolean function or this logic gate design as at the gate level description. Let's try to compile it. Oh, okay, 2 errors. Let's see. Time scale must be at least precise a time unit. Okay, yeah, I was just okay. So maybe this is the forward slash. Is it?
Is it because you put picoseconds instead of nanoseconds?
And now it is that 2 different thing. What is that?
The time step and the precision.
Yeah, let me just try to see. open up one file and see. Just hold on.
Is that, I don't even know what that symbol is called, but the sort of apostrophe looking thing before timescale is supposed to be there?
Yeah, that backtick's supposed to be there.
Okay.
So let me see. We should have. Okay. So it is the other way, basically. Got it. So it has to be like 1 nanosecond by 1 picosecond. So 1 nanosecond is the 1 unit, and this is a simulation resolution, 1 picosecond. I hope that would solve the problem.
I think it had 10, no?
No, this is like an this is a precision part, like more. Actually, we can make it 10. 1 picosecond means the simulation time step would be like per 1 picosecond, 10 picoseconds, which is basically okay for the digital simulation. Here is we are saying that okay, my scale simulation scale is 1 picosecond, and nanosecond. This part means basically if I do a time stamp like this, £5, that means it is 5 nanoseconds. So that's the unit is coming from here. Okay, and this unit is basically is the internal to the simulator setting, that how precise you would be on the timing point of view of the digital circuit. So I think 10 picosecond is better, because if you make it lower, like 1 picosecond, simulation time may be longer. For the smaller circuit, it doesn't matter. For the bigger circuit, it does. So, so let's see. Yeah, this is successful. Now we want to make a test bench around it to test this circuit, what we just made. What does it mean is that we pick up this circuit. Okay. Let me just remove this whole thing so that I can draw a little bit cleaner. Okay. So my AND X inverter W1, this is Y, W2, Z, and F. Now test bench means we will be enclosing or instantiating this circuit, okay, and we'll be driving, there will be some driver which will drive the values, input values, like maybe let's say we want to test with this guy. So X will set to 0, Y will set to 1, and Z will set to 1. And then this whole Verilog model will evaluate that logic internally, and should give a logic value of 1 here. Okay, so that's the test bench. This whole thing, whole setup is a test bench. So in the test bench, what then we have? We need to drive some input. So this calls for something like register. And we need to observe the output out of this. So maybe let's call it a where. So register, maybe we can name it as a X reg, Y reg, Z reg, and where maybe we can just make it as an WF, something like that. And then we need to instantiate and connect. So to do that, we need to add another file. Let's change it to the Verilog. And file name, you can give any file name. There's a myfunc underscore tb. That's the file name going to be. And here, what we do, we basically define the time scale module. You can give any name, but I'm picking up myfunc tb, and there is no IO port there. It is self-sufficient and module. And here we are defining some register named X reg, Y reg, Z reg, and a where name, let's say, that's what we say, WF. Then we instantiate this block. Let's take out this block, myfunc. So myfunc, let's say instance name is mf1. Then we connect these registers, to the port, right? Port name is X, Y, Z, etc. So what we can do, we can explicitly name them. X means connect X to X reg, Y, so connect port Y to the Y reg, connect port Z to the Z reg, and connect port F. Was it F? Yeah. F to the WF. So this is explicit connection. And if you do the explicit connection, you need not to keep the order of the port. So here, see, the order of the port is F, X, Y, Z. But here I have connected in order of X, Y, Z, F. Because I can do that because I'm explicitly specifying the connection. The alternate way would be like this. Myfunc mf1 this is the implicit connection. X reg, Y reg, Z reg. Okay, so implicit connection is a kind of a shorthand notation, but you need to make sure that this sequence actually follows the sequence of the port. So that's why I personally don't like this way, though it saves typing, but it can lead into some like unforeseen error on doing it. But both ways are perfectly okay. All right. So far, any question?
I have a question like about like the connections. Can you connect? So in myfunc TV, can you connect like one of the variables here to a wire in the myfunc? Like you connected it to the to the X, Y, and Z in myfunc. Like you connected to one of the wires there, like W1 or W2. Is that possible?
So the thumb rule is that if it is an input port, it must be driven by a register at some point of time. It may be the case that this guy, instead of register, like it may be some advanced test bench or something like this. Like I have the instantiation, that is, we call it design under test or DUT, design under test, design under test, and other part is test bench generator. So that itself is maybe a circuit, digital circuit, and they are connected via wires. Okay, and let's say this is the input side. But point is that at the end of the day, it must be driven through from our register. Is that clear, Kevin?
So you're saying that like we have the test bench and is connected to myfunc through the wire. So this is like implicitly there's a wire between the two ports. So between X and X reg, there's an implicit wire there.
Oh, okay, okay. Yeah, that's the implicit assumption that this X reg is connected to export means like logically there is a wire existing, and you can think of that wire name itself is X underscore reg. So you don't need to connect it register to the wire, then wire to the port. You don't need to do that.
Thank you.
Okay. And the other thumb rule is that if it is an output port, you are not allowed to connect it with a register. That will give you a compilation error. Okay. Now, what we'll do, we'll try to mimic or supply these set of values into that system. Okay. So how do we do it? Look, we start with the init block, initial, begin, end. Okay. Now let's put some values. So at the very beginning, you don't need to specify that, but just let's see if it can handle it. X0 is 0. And here, to be very precise, we want to put it's a single bit 0. So with this one, binary type value 0. Similarly, this guy, that's followed by a semicolon, 1 tick 0, zreg equals 1 tick 0. So everything is 1 bit. Now let's say after 5 nanosecond, we keep on changing things. Okay. From there, after 5 nanosecond, we'll make it 1. Then after 5 nanosecond, we'll make it 1, 0, 1, 1, 0, 1, 1. Then we'll keep 1 as X as this. Okay, so we are driving the test bench. Let's see if we can compile. Oh, okay, error. What's that?
On line number 9, aren't you supposed? I think the comment is the forward slashes instead of the pound sign.
Thank you very much. Yeah. Okay, that's good. So we did that. Now let's see if we can run it. So to run it, we go to the library tab, open up the work, and open the myfunc.tv. myfunc.tv. So it will bring you another window, another layout of the window, where basically this is a simulation object where my function is instantiated. It has inverter and all this stuff. And it has, what we can do, we can actually, this is a top level. This is, look at the range and WF. Let's observe it. Okay. So what we do is select all, like you can hold the shift key and just move over the mouse there, right click, add wave. So it will be added onto the wave. And in fact, you can actually go inside and look at its own wires value for the debugging if needed. But let's not do that right now. Let's stick to this one. And then, oh, I wanted to do one more thing we need to do. Otherwise, we won't stop it. Okay. $5 stop. So this means at that point, the simulation will stop. Let's recompile it. Where is my compile all? And since I recompiled, I need to reset everything. Okay. All right. Now simulate. Run all. So it stopped at this point. We have some waveform. It's too big, so let's minimize. Where is that? Here. Fit all. Okay, so what we see here, we see that at this point, my XYZ is 0 and my outcome is 0. Let's tally with what we had at the truth table. Okay, let me just undock it. That will be good. Okay. Fit all. Okay. 0, 0, 0, and then we are changing the Z to 1. So at that point, it become 1. So 0, 0, 1 is 1. Now 0, 1, 0 is 0. It's tallying with this. And then we change it to 0, 1, 1. And we have 1 back. Then 1, 0, 0. We have the same 1. And then we have 1, 1, 0. Or what is that? 1, 1, 0, 0. 1, 0, 0 is 1. Then 1, 1, 0 is 0. And 1, 1, 1 is 1. So we can see that our circuit is working. Whatever we implemented as a Verilog hardware description, that basically working as expected. So this way you can, this is the start of your gate level modeling, and we'll pick it up after the project 2. Project 3 will be modeling like this. And but when we are studying this digital component and etc., you might want to experiment yourself with writing a little bit of these gate connections and look at the functions and all this stuff to make understand more on top of the theoretical study on these logic components. Question so far?
So
okay.
I have a question. So why do you put initial and begin for the test bench?
This one? Okay,
Yeah.
initial blocks is more like giving you that this is a piece of code that will be running in parallel with this piece of code. So Verilog is everything is running parallel. So when you are simulating the whole system, this module is running parallel, waiting for these inputs to get changed so that it evaluates the value, so that your instantiation is running in parallel with this block. And this block is somewhat giving you the time-lapse logic changes. Like this is first logic, and then it basically go with every 5 nanosecond it changes the logic combination. So it is supplying, this block is supplying the logic values to this block. They are running in parallel with each other. Is that answer your question?
But what's the difference between the initial and begin here? So what's the purpose of each of them? So I know that they run in parallel.
Okay. So this is basically like your C or Java code's open brace, and end is C or Java code close brace. So you are defining a block of code here. Kevin, does that make sense?
So, yeah, I get that there are brackets, but is this the only situation where you would have to do like the initial and ending, like those brackets? Is this the only situation, or like, oh, when do you need to use these brackets? Why can't you just like do begin and stop without the brackets?
Begin and stop. Okay, so basically this is a block. So anywhere you need to write a block of code has to go under begin and end. So it doesn't necessarily need to be under the initial. Okay, so initial is a block which can be like this as well. Like let's say just one-liner code, like xreg was 1 bit 1, just one-liner code. Okay, but it can only cater one statement, Verilog statement without a block. Okay, this is one-liner statement, but as soon as you want to include multiple Verilog statement under one specific block, like initial, there is another block called always. There are another block that switch case statement can have a block of code. So for those things, you need to define as a block of code, which always has to be between begin and end. Am I like making sense, or can you explain your question like a little bit more detail? And if you can be a little bit louder, please.
Yeah, so you have so you're saying if we only need to do one line, then we only need initial?
Okay, initial is a Verilog construct. Okay, this means that the initial, a code following the initial statement will be executed at the beginning of the simulation. That's what the initial means. Okay, there is another construct, but always maybe at pause edge, these kind of things. Like yeah, probably you want to go through the other Verilog tutorials for the behavioral modeling, something like this. So this is the always block. It will be followed by a piece of code. Like if that code is one-liner code, you don't need a begin end. But if it is that always code block has to be a multiple line code, then that code has to be within a begin end statement. So begin end, and this is like statement 1, statement 2, like this. So there are multiple scenarios where you need to write this begin end statement in the behavior modeling.
I see.
Okay. So there would be like switch case, and if then is another part where you might want to have these begin end blocks, like it encloses like multiple statement together. Just it is equivalent to your high level like C or Java programs open brace close brace code. Basically, it's a block of code.
And like the stop, the $ stops ends the register, like the register.
So this, yeah. Okay, this is we call it a macro. So anything start with a dollar in Verilog is called a Verilog macro, and it has a specific function. So $stop, what it does is basically stops the simulation at this point. So when simulation execute these and these next statement after these time steps, and whenever it comes here, it stops there. So remember, like in the simulation, right? It's let's see. Where is that? Okay, let's reset. And run all. So look at this. It basically, why it is, oh, basically I changed things. That's why. Okay. It's stopping at the stop point. Let me decompile. Just hold on. Otherwise you'll be confused. Recompile, reset, and run on. So see, like, assume this, your execution is basically going through statement by statement on line 13, 14, 15. And as soon as it hits the statement on the line 21, it has a $stop. It stops the simulation. Otherwise, what would happen? Let's experiment it. Let's take them out. Okay, let's take it out. Compile. And reset. And run on. What it is doing. Did it end? Just hold on. Reset. Okay. Compile. Reset. Okay, let's do one thing. End simulation. Okay. And reload. Okay, let's make sure we save this whole thing. Compile all. Load the functions. And hit the run all. Oh, just wait a minute. It should not terminate. Where it is getting that termination? Just hold on. Oh, maybe the new revision actually has a stop at the end. Ah, that's interesting. I was hoping that to show you that the simulation will never stop, but since like this is a newer revision, it basically stops at the end of the initial block. That's nice to know. But anyway, wanted to have that stop. It's safe to have the stop there at that point. Okay, Kevin, I'll get back. I'll study this more about stop and not stop, and I'll get back to you guys. What is the new behavior about this simulation? Okay.
Thank you. Thank you.
So any question so far? Actually, we are actually out of time, basically. Almost 2 minutes to go. So any last minute question?
You said that it's because of the new revision that it now stops at the end of the initial block. Do you know if that's a Verilog edition or a model sim edition?
I don't know. I need to research that.
Okay.
I'll find out what is going on there.
Professor, are you going to post this code snippet?
No, I'm not planning to. You might want to write yourself, right? What's the, I'm recording this video. So basically go and snip it. Yeah, snapshot it.
Okay.
Okay, so remember the next Monday is a holiday. So we no classes for next Monday. And we'll then all meet you on the Wednesday then. Good night, everybody.